This is review video 28. What is kinetics? To put it broadly, the study of kinetics is the study of how fast a reaction can go. More specifically, when we look at kinetics, we're going to study the rate of reaction, which is how fast it goes, as well as anything that could influence that rate. In addition, when people study kinetics, they also study reaction mechanisms or the individual steps of reactions. And another way to say reaction mechanisms would be the reaction pathway. So specifically, what's reacting with what atoms are breaking apart, what atoms are coming back together, etc., etc. Reactions can be fast, they can be slow, they can be mid-range. Examples of a fast reaction would be a bomb, is the best example. Fire is a pretty quick reaction, even though fires can burn for a while. And slow reactions would be reactions that happen over a really long period of time, like, for instance, rusting. Rusting is more specifically known as oxidation, and that reaction takes a while to really happen. So how exactly do we study how fast reactions go? What do we pay attention to, etc.? And collision theory is something that we always pay attention to when we're looking at kinetics, and it's a theory that addresses how molecules have to interact with one another to react successfully. Because not all molecular interactions result in a chemical reaction. You have to have enough energy to react, you have to hit each other correctly to react, you have to do all of these things to actually react with one another, that if two molecules interact with one another and they don't meet a specific criteria, they're not going to react with one another. So the main tenet of collision theory is that not every single particle collision or interaction is going to result in a reaction. There's three main points of this theory. The first is that to react, two particles have to hit each other. They have to collide specifically to do that, and that's pretty obvious. So that's tenet one. The second main point is that particles have to hit each other with enough energy to react. And what do I mean by that? So we just talked about potential energy graphs. If those two colliding molecules are not colliding with enough force to meet or exceed the activation energy of the reaction, E sub A, then they're not going to react. Point number 3 is that particles have to hit each other with the correct geometry to react. And by geometry, I mean the right angle, right? So this little graphic over here shows you particles hitting each other from different angles, and some of them produce a reaction and some of them do not. So we see this NOBr molecule hitting another NOBr molecule kind of side to side, and that is a sufficient angle to break the bond between the N and the Brs, and for the Brs to come together. If they hit each other end to end with Br, then hey, guess what? That's enough energy to break the bond between the N and the Br and for the two Brs to come together. Amazing. That's the correct angle for that. But if they hit each other end to end on the O side, then there's not enough energy on that geometry to break the bond that's between the N and the Br. So actually no reaction occurs if the molecules hit each other like that. Other things that we look at in the study of kinetics are factors that can influence the reaction rate of specific chemicals. So the first one is going to be physical state. And by physical state, I literally mean, are those things that are trying to react with one another solid? Are they liquid? Are they gaseous? Or are they aqueous? Because some molecules can react in aqueous form, but not in solid form. Some molecules can react in liquid form, but not in gaseous form. It kind of depends on the reaction that you're doing. So the example I have for you here is a precipitation reaction. We have silver nitrate, AgNO3, and potassium chloride. And the reaction is showing you that to react successfully, those particles have to be in aqueous state. They have to be dissolved in water. Because if you were to mix those two things as a solid, as two powders, they're not going to do anything. They're just going to chill in the same beaker and not react at all. But if you dissolve them in water, suddenly we now have enough energy, we have the right angle for those things to react with one another and for the silver chloride to precipitate out of that solution. So again, physical state has a lot of influence on reaction rate. It can take a reaction from going basically zero to going very quickly. Another thing that can affect reaction rate is concentration. If you increase concentration, what you're doing is you're putting more reactant molecules in the same space, and you're increasing the probability that reactant particles can hit each other. So you're increasing the probability of a collision happening. So this graphic over here is showing you a low concentration where the molecules are there, but they have a lot of free space and they're not going to hit each other very often. And you might get one particle collision in one reaction, but the other ones are just chilling. But if you increase that concentration, if you pack more molecules into the same space, suddenly you have more instances of collision. And so you're going to speed your reaction by doing that. If you decrease concentration, you do the exact opposite. You slow down a reaction. Another thing you can mess with is temperature. So at a low temperature, molecules are going to be slow, right? And we know based on collision theory that slow molecules are less likely to hit each other with enough energy to react. But if you increase the temperature, suddenly those molecules are going to move faster, and therefore they are going to hit each other with more energy, and it is more likely for them to hit each other with enough energy to react at that point. All right? So by increasing the temperature, you're just making those molecules more likely to react with one another and therefore speeding your reaction up. Another thing you can mess with is surface area. This one's a little wonky to think about, but if you increase the surface area of your reactant molecules that are exposed to one another, you are increasing the likelihood that those particles can interact with one another at all. And so the example I usually give is think about dropping a sugar cube into your coffee or tea or whatever versus dropping granular sugar into your tea or coffee. This graphic kind of helps you understand what's going on there. So let's imagine that the blue ones out here, those are the coffee. And let's imagine that the pink ones are our sugar, okay? So all these sugars on the outside of the cube, those can interact with the coffee, right? Because we can get a particle interaction between that. We can get a particle interaction here. We can get a particle interaction there. But the issue with the cube is that all of these ones on the inside are incapable of colliding with the coffee molecules. So they can't react, they can't dissolve, because they literally can't even touch the coffee molecules. And we know, based on collision theory, that particles have to collide to react. However, if you envision breaking that sugar cube up, mashing it down into granular sugar, suddenly we have much smaller pieces, but more surface area is exposed, right? Because all the way around is exposed to the coffee molecules. So all those dark pink ones that were hidden in the cube, they're now available on the surface, and we can get particle interactions with all of that now. And so you are going to speed up your reaction by making it easier for those reactant molecules to interact with one another. All right. The last thing you can mess with to speed up or slow down a reaction is a catalyst. You can add a complete new chemical to a reaction that might speed up or, in rare cases, slow down a reaction. What a catalyst is a chemical introduced into a reaction that A, is not consumed during that reaction, or you can have a catalyst that is consumed and reformed at the end. But B, more importantly, that catalyst is going to provide an alternate reaction pathway or mechanism. And that alternate reaction pathway has a lower activation energy requirement than the original reaction. So by adding a catalyst, you're providing an alternate pathway that's easier to do. And so therefore, it's going to speed up the reaction. This reaction, the decomposition of hydrogen peroxide, is something I'm going to show you in class, and I'm going to show you the catalyzed version as well. But the main reaction that we're doing is we're taking an H2O2 hydrogen peroxide and we're breaking it up into water and oxygen gas. It's an exothermic reaction, so it's going to release heat energy overall, but that's not important right now. The mechanism for the uncatalyzed reaction looks like this. We take the H2O2, we break off an oxygen, and leave a water behind. And if you do that a bunch of times, you're going to end up with a lot of singular oxygens around, which will bond together to form O2. And we know that that happens because O2 is a diatomic element. And so they always pair up when they are in samples of themselves. So that's the uncatalyzed mechanism, and it looks really simple to do. But the problem is there's a pretty strong attraction between H's and O's, right? And so to actually break off that oxygen takes a ton of energy, and it's going to happen very slowly because hydrogen peroxide just chilling by itself with no other chemicals is pretty stable. It just sits there. You all had hydrogen peroxide probably under your bathroom sink for a really long time, and it just stays there and it doesn't do anything. However, if you want to speed up the decomposition of hydrogen peroxide, you just have to add a catalyst. Specifically, manganese dioxide is a really good catalyst for this reaction. And at first glance, this mechanism here, this reaction pathway, looks insane. It looks crazy because it looks like all of this is far more complicated than the original mechanism. And to a degree it is. But the key here is that the interaction between those chemicals literally makes the energy requirement of that reaction a lot less, and it makes the reaction easier to do. And so effectively at the end, you end up with the original catalyst, you end up with H2O, and you end up with O2. Now, in terms of why I'm circling products that are in different steps, we'll go over that when we get to reaction mechanisms, which is going to be later in this unit. But trust me when I say you end up with the same products you started with, and you end up with a catalyst that has not been consumed by that reaction. All right? Here is the potential energy graph that represents both the uncatalyzed and the catalyzed versions of this reaction. So the red line on top, this one that I'm currently highlighting, that one represents the uncatalyzed mechanism. So we can see that its activation energy requirement, just dotted line that, it's pretty significant. It's a pretty steep hill. However, if we look at the catalyzed mechanism, which is this wonky little guy right here, neither of its hills are very tall. So step 1 of that reaction doesn't require very much energy at all. Step 2 of that reaction requires just a little bit more. But either way, neither of those activation energy requirements are quite as high as the uncatalyzed one. So in so doing, in reducing the activation energy, we have made it easier for molecules to react with one another, and therefore we have sped up the reaction by adding a catalyst. All right? If you are asked to draw a catalyzed potential energy graph, you don't have to do anything with these mechanistic steps. You don't have to create a complex looking hill or anything like that. You'll never be asked to do that on the AP exam. All that you have to do to represent a catalyzed reaction is you have to draw a smaller hill, right? So let's say that your question on the AP test has this hill and it says, okay, here's the uncatalyzed reaction, draw the catalyzed one. Well, all you would have to do is start in the same place, make a smaller hill, and end in the same place. That's it. It's never going to ask you to be specific with how much energy reduction there is, because it's rare that you would even have that information. You just have to draw a smaller hill. If you have any questions about catalysts specifically or anything else, please ask me in class.